Let's say you're a quality control engineer working at Norman's fourth largest cracker factory, and you're monitoring quality with a control chart for nonconformities that is based on a Poisson distribution. How do you know what the rate of occurrence is of that particular phenomena that you're collecting data for? Or say that you're a reliability engineer at Kruger Industrial Smoothing, and you're monitoring the lifetimes or the times to failure of bearings machined at Kruger. A common probability distribution for describing this uncertain measure, the time to failure, is the exponential distribution. But how do you know if the failure time data are exponentially distributed? Maybe failure time is more effectively described with a Weibull distribution, similar to the exponential but not quite the same. How do you know what the best parameters of an exponential distribution would be, or the best parameters of a Weibull distribution? We need a way to fit a probability distribution to a set of data. By fit a distribution, we mean find the best distribution parameters that match the data to the distribution. There are several ways to fit a probability distribution to a set of data. Among them are the method of maximum likelihood, the method of moments, and the method of least squares. Each of them are appropriate in their own way depending on the probability distribution. We're going to focus on the method of maximum likelihood in this unit. Let's talk about a small general example. Say there's a phenomenon whose measure is described with a random variable y. We want to find a good probability distribution for y because doing so will allow us to find the probability of a particular interval of y. So we go collect some observations. For the purposes of this illustration, say we collect 3 observations, y1, y2, and y3. Naturally, that's a small sample, but we want something easy for this illustration. The way we approach the method of maximum likelihood is by assuming what the distribution is. That is, maybe based on a histogram of some sample data or based on what we know about the phenomenon that we're describing, we can first assume a distribution, like an exponential or a normal distribution. We only talked about a handful of possible distributions in this class, but there are many. Regardless of the probability distribution that we choose, let's say that the PDF is f of y. We need to define something called a likelihood function. The discussion of this can get a little complicated, so let's gloss over a few details and terminology, and just say that the likelihood function is the joint PDF of all of our observations given the parameter of the distribution that we've chosen. We write the likelihood function as the multiplication of the PDFs evaluated at each of the n observed values given the distribution parameter, or set of parameters, theta. In our simple example, the likelihood function is f of y1 multiplied by f of y2 multiplied by f of y3, all of which are evaluated given the distribution parameter theta. Again, theta is the general notation for the distribution parameter parameters. If we were fitting an exponential distribution, we'd use lambda, the rate of occurrence. Or if we were fitting a normal distribution, we'd have 2 parameters, mu and sigma. So now we have a likelihood function, and we need to find the optimal value of theta. What's the best theta to fit a distribution to our sample data? We said that we're going to use a method of maximum likelihood, which means that we want to find the value of theta that maximizes our likelihood function. How do we maximize a function subject to a variable? We use calculus. We take the derivative of the likelihood function, set it equal to 0, and we solve for theta, or that distribution parameter. Easy enough. Except one issue. We would have to implement the chain rule a bunch of times because our likelihood function is a bunch of PDFs multiplied together. To help our cause, we usually take the natural log of the likelihood function and then take the derivative. The natural log of a bunch of functions multiplied together is equivalent to the sum of the natural log of those functions. Also, finding the maximum of the likelihood function is equivalent to finding the maximum of the natural log likelihood. Again, what we're doing is maximizing the likelihood that y1 through yn were sampled from the probability distribution with parameter theta. What value of theta gives us the best chance to have pulled our sample from that distribution? Say we want to fit an exponential distribution to our little sample of y1, y2, and y3. Our likelihood function would be the exponential PDF multiplied by each other, evaluated for y1, y2, and y3. We can take the natural log of the likelihood function to get something a little more manageable to take the derivative of. We'll work out some examples with data a little later on, but for now, hopefully you get the idea. So this is the method of maximum likelihood. The optimal distribution parameter or parameters that we fit to our data set are called maximum likelihood estimates, or MLEs. Again, we have to assume a distribution to start with, as we're finding the optimal parameters, assuming that distribution. We'll discuss goodness of fit tests later on to see how good of a choice that particular distribution is.